Hi, my name is Bahadur Ahmedov. In this video lecture, we are going to discuss about the linearly dependent vectors. So if I give you two matrices, A and B, if I say, hey, could you please calculate me determinant of these matrices, you can calculate this using the formula when you multiply 1 to the 4 and subtract 2 times to the 3, which is going to be equal to the minus 2. Or you can calculate determinant of this matrix, which is going to be 1 times to the 2 minus 1 times to the 2, it's equal to the 0. And it's somehow clear that the determinant of this matrix B is equal to the 0 because the second column is very similar to the first column, right? So in this case, we say that the second column can be obtained by just multiplying the first column to the 2 or by just some linear combination of the first one. So we call these two columns as the dependent columns. And we kind of feel that they are dependent, right? So let us write down the intuitive definition of the dependent vectors. So let's say you are given three vectors, v1, v2, and v3, and they're called linearly dependent. They are dependent, linearly dependent. If one of the vectors can be obtained as the combinations of the other two. If one of the vectors can be obtained as a linear combination of others. So this is what we felt about this matrix, right? So the second vector here, v2, can be obtained as the combination of the v1 when you just multiply the v1 simply to the 2. So this is a very intuitive definition of the dependent vectors. So what I want is I would like to give you an example when we can express one of the vectors as a combinations of the other two, and then try to derive more solid, more technical definition of the dependent vectors. So let's say we are given three vectors. V1 is given as 1, 2, 3. V2 is given as 0, 1, and 3. And V3 is given as 2, 5, and 9. So at the first glance, you probably don't see that these three vectors are dependent, but if you look a little bit more in details, more carefully, you can see that the third vector here, 2, 5, and 9, can be obtained as the combination of the first two. 1, 2, and 3 can be multiplied to the 2. 0, 1, 3 can be multiplied to the 1. And if we add them, we are going to get exactly the third vector. So essentially, if you multiply this first vector to the 2, you're going to obtain 2, 4, and 6. If you multiply the second vector to the 1, you're going to obtain 0, 1, and 3. And if you add them, you're going to get exactly this vector, which is 2, 5, and 9. So you see, so by combining the other two vectors, we've got the third vector. And actually, there are infinitely many combinations which can bring you the third vector. And this is what I mean by saying the infinitely many combinations. So here, 1 times the third vector is equal to the 2 times the first plus 1 times the second, right? So let us write this down. So the third vector can be obtained as the linear combination of the other two. So I'm going to put the two lines here in order to denote that they are the vectors. So the third vector can be obtained by multiplying the first vector to the 2 and the second vector to the 1. But at the same time, you could multiply the first vector to the different constants. For example, you could multiply this to the 4, and this can be multiplied to the 2 in order to get 2 times to the v3, right? And this is another combination which brings you to the v3. So there are lots of combination which can bring you to the v3. But what I want is now I would like to try to derive the more solid definition of linearly independence or linearly dependence. So if I would put all of these vectors to one side of the equation, what kind of equation we would get? We would get 2 times the v1 plus 1 times the 0, so this is v1. So 1 times the v2 minus 1 times the v3 is equal to the 0, right? So you see, so you are multiplying, you are finding a linear combination of the 3 vectors, so that this is equal to the 0 vector, right? And this linear combination contains non-zero coefficients. So this is a linear combination, a linear combination, which brings you to the 0. Well, this is going to be the solid definition of the dependent vector. So essentially, if you can combine the vectors so that it will give you a 0 vector, then these vectors are going to be called as a linearly dependent vectors. So I'm going to show you a small example, and then we're going to write down the definition. So let's say if you remember, the first matrix was 1, 2, and 3, and 4, right? So it was the A matrix, if you remember from the beginning of the lecture, and the B matrix has the columns 1, 1, and 2, and 2, right? So could you please tell me the coefficients before the vectors for the second matrix B, so that the combination is going to give you 0 vector? Well, it is easy. You can multiply the first one to the 2, the second one to the minus 1. It will give you 0 and 0. You can find other combinations which will give you the 0 vector. While for the first matrix A, there is no such a combination which gives you 0 vector. So you cannot obtain 0, 0 by combining these two vectors unless you're not combining them with the 0 and 0 coefficient. So this is the only combination. Only combination, right? And here you can find infinitely many combinations. A combination, one of the combinations. And this is independent vectors, independent, and this is dependent. Okay, so by just looking to these examples, we can figure out the definition of the dependent vectors. So let us just write this down. So a set of vectors v1, v2, and so on, vn, is called linearly independent, is called linearly independent if the only coefficients, A1, A2, and so on, An, that satisfy the following that satisfy the following equation. Essentially, you are going to combine the columns of this matrix with the coefficients. So the first coefficient A1 is going to be multiplied as the first vector, plus A2 is going to be multiplied as the second vector, and so on. The last coefficient is going to be multiplied as the last vector is equal to the 0 vector. So the only coefficients A1 and so on, An, that satisfy this equation are simply the zeros. So this is the only way of combining these vectors in order to get the 0 vector. So if you remember, here it is. So these two vectors are linearly independent, and the only pair of the coefficients which brings you the combination to be equal to the 0 vector are the 0 coefficients, right? And this is the definition. If one of these coefficients are not equal to the 0, if at least one of them is not 0, then these vectors are linearly dependent. Then this set is linearly dependent. Well, this is the definition, but now we need to figure out how to do this technically, right? So essentially, what we are saying, hey, if you have three vectors, v1, v2, and v3, we are saying, hey, could you please combine them and try to get, so combine them, for example, with the three coefficients a1, a2, and a3. If you remember, if you multiply this matrix to this vector, it's going to give you exactly the combination, right? A1 times is a v1 plus a2 times is a v2 plus a3 times is a v3. So this is what does it give you, this multiplication. And this should be equal to the 0, 0, 0. And if you remember, we call this kind of equations as the homogeneous equations. Ax is equal to the 0, right? So you need to figure out whether this system of linear equations is going to have a non-trivial solution. If it has only the trivial solution, basically, if x is equal to the 0, if all of these coefficients are equal to the 0, we call this as a trivial solution. If it has only the trivial solution, then the three vectors are linearly independent. If it has a non-trivial solution, if this x vector is not equal to the 0, it means that one of these entries is not equal to the 0. Non-trivial solution. Then the columns of the matrix A or this vectors are linearly dependent. So this is how we are going to identify linearly dependency technically. Okay, so now from the beginning of the lecture, we define the intuitive definition of the linearly dependency, then we figure out the solid definition of the linearly dependency. Now we are discussing the algorithm of finding the linearly dependent or independent or check whether the vectors are linearly dependent or not. So let's do two examples to show this. So one example is going to be you're given a matrix A was the three columns 1, 2, 3, 2, 2, 6, 3, 7, and 10. What you need to do is you need to figure out whether the columns of this matrix are linearly dependent or not. So essentially, this is V1, this is V2, this is V3. Whether they are dependent or independent. Okay, so in order to do this, you need to solve the equation Ax is equal to the 0 and find all the solutions. If it has only the trivial solution, then it is going to, the columns, these three vectors, are going to be independent. So in order to solve the system, we need to bring this matrix into the row echelon form, right? So in order to bring this to the row echelon form, we choose the pivot on the first row, and we're going to eliminate everything below this. We multiply the first row to the minus 2 and add this to the second in order to eliminate this 2. We multiply the first row to the minus 3 and add this to the third row in order to eliminate this 3. So let's try to do this. So if we do this, what we get? So I'm going to copy the first row as it is. If you multiply all of the three entries on the first row, 1, 2, and 3, into the minus 2 and add this to the second, what you get is 0, minus 2, and 1. If you multiply all of these entries on the first row to the minus 3 and add this to the last one, what you get is 0, 0, and 1. So essentially, it is really easy for us to bring this to the row echelon form, right? So what we have to do is now we are going to make this minus 2 to be equal to the 1. So in order to do this, oh, it's already clear that this matrix is already in the row echelon form. So this is in the row echelon form. And we can try to solve this equation, right? So the last equation is going to tell you 0 times the x1 plus 0 times the x2 plus 1 times the x3 is equal to the 0 because the right-hand side part was the 0 vector here, right? Okay, so the second equation is going to tell you 0 times the x1 plus minus 2 times the x2 plus 1 times the x3 is equal to the 0. And the first equation is going to tell you, that 1 times the x1, 1 times the x1 plus 2 times the x2 plus 3 times the x3 is equal to the 0. So if you find a solution, it's going to have you like x3 is equal to the 0 from the first equation, x2 equal to the 0 from the second equation, and x1 is equal to the 0 from the third equation. And the only vector which satisfies this equation is simply the 0 vector. It has only the trivial solution. So that is why the columns of this matrix are linearly independent. And it was kind of clear from the row echelon form that they are linearly independent because all of the columns are going to have the pivots. All columns have the pivots. Columns have pivots. So we can also connect this with the rank. So all of the matrices with the full column rank have the linearly independent columns, right? So now let's consider an example of linearly dependent columns. So let's do another example. So if you're given a matrix B with the columns 1, 2, 1, 0, 1, 0, 3, 5, 3. And again, you have to multiply this to some vector x and equalize this to the 0 and find the solutions. Find all of the vectors x which satisfy this. If it has only one solution, the trivial solution, then the columns are linearly independent. If it has infinitely many solutions, then it has dependent columns. So again, we are going to bring this matrix into the row echelon form by eliminating this 2 and eliminating this 1. We can multiply the first row, right? So this entry 1 should be multiplied to the minus 2 and added to the second. And this row should be multiplied to the minus 1 and added to the third one. And which will bring us to the matrix 1, 0, 3, 0, 1, minus 1. And if you multiply all of the entries on the first row to the minus 1 and add this to the last one, you're going to get 0, 0, 0. Well, you see, so not all the columns have the pivots, right? So the first column has the pivot, and the second column has the pivot, but the third column doesn't have the pivot. So it has the free column. So it has the free column. And if you remember, if a matrix has the free column, it means that it has a free variable. It means that it has the spatial solution. So that is why the null space is going to have infinitely many vectors. So it means that you are going to find infinitely many vectors x, which makes this multiplication to be equal to the 0, or you can find infinitely many combinations of the 3 vectors, which will bring you to the 0 vector. Well, this was the discussions about the linearly dependency and independency, its definitions, intuitive definitions, more technical definitions, and also the algorithms of identifying linearly dependency or independency of the vectors. So I hope that this was helpful.